So there are some interesting observations you're going to see in this equation. One observation is all the quantities that appears as coefficients, right? 1 over delta times d delta dc, 1 over ue times due dc. They are all 1 over something times d the same thing, dc. And from our previous experience, we know that all of these quantities grow or decay. I mean, they all grow. They grow as a function of a power law of c, right? And what does a power law mean? Do you remember if we plot in the log scale, log of ue, for example, log of c? What does a power law mean? It's a line, right? Meaning d log ue over d log c is a constant, right? Okay. So right now we have d log delta dc, d log ue dc. How do we make it the ratio between two d logs? So that I know if I have a similarity solution, these would be constants. Okay, how do I get, for example, d log delta over d log c? Well, you go expand it, right? D log delta is equal to 1 over delta d delta. And d log c is basically dc, and I put a c here, right? So, in order to get this kind of constants, can I just multiply everything by what? By c, right? So I multiply c on this whole thing. I have a c here, I have a c here, I have a c here, and I have a c here. That's good, because now, okay, let's look at the entire left-hand side. The entire left-hand side corresponds to derivatives. They only appear when you have a derivative with respect to c, right? For similarity solutions, the whole left-hand side vanishes. This is kind of the memory term of the boundary layer. If I have a profile that is close to separation, for example, after you drive it with a favorable pressure gradient, it will not immediately become like Blasius. It'll lag for a while. And this is the term that is responsible for that, because it has derivatives with respect to c. The entire right-hand side has no dependence on the derivative of c. So that if I set the left-hand side to 0, I get the similarity solutions, right? For example, if I want to solve this equation at the leading edge, c is equal to 0. So the whole left-hand side goes to 0. That's convenient. And I exactly have the Faulkner-Scain equation for me to solve, right? Okay. And so this is good. And another observation is that this coefficient is nu c divided by ue delta square, right? And in Faulkner-Scain solutions, we do remember that there are scaling laws, like the delta goes proportional to x over 1 over 2 plus alpha, and our ue goes proportional to x alpha over 2 plus alpha. And if you plug these relationships exactly into this, I mean, other than replacing x with c's, you basically get the fact that the delta, the big delta here and the small delta here, whether we define it to be the location where my eta is equal to 1 in Faulkner-Scain equations, or if I define my delta to be the displacement thickness, they are on the same scale. Okay, which means this is a nice quantity that I can somehow define my delta so that this is equal to 1. Alright, so what if so here the idea is, what if I define, because I didn't say what big delta is, right? I only said big delta is a function of x. Now I'm going to define my big delta so that it is equal to the square root of nu c divided by ue. You can check a few quantities, like you can check what if I have the Blasius solution on a flat plate. My ue is equal to constant, and this delta is going to get me a scaling law that is square root of x, right? So that's good. And also you can check for a leading edge stagnation point flow. I have ue to be exactly proportional to x. In this case, I'm going to get a square root of a constant, which is constant. That is going to give me roughly the order of the thickness of the boundary layer starting from the leading edge. So let's do that. So if we define it that way, all right, and we can take the logarithmic. Okay, so this is convenient, not only setting this to 1, but you can take a look at here. I have delta related to c and ue, where nu is a constant. That is actually going to relate me these two terms that appears in the thin layer equation. So I can know that one term is exact a function of another. So for example, it's easy to take log on both sides. So my log of delta is equal to a half of log nu, which is a constant, plus half of log c minus a half of log ue, right? That's basically expanding this equation in logarithmic. The square root becomes a half. Any power becomes a multiplier after you take the logarithm. And once I take the derivative of this constant goes away, right? I have derivative of d delta over delta. That's the derivative of, that's a small change in the log. Is equal to, this goes away, 0 plus half of dc over c minus half of due ue, right? Okay, so now what is that? This is basically saying that I can obtain this term by dividing both sides of the equation by that, right? So I can obtain exactly this term in the equation. Okay, c over delta d delta over delta, d delta over dc is now equal to a half times 1 minus this term, due dc, right? So we are actually writing this term as half of 1 minus that term. And this entire parenthesis now becomes half of 1. The minus half cancels with half of this 1 term, so I become plus cue due dc, right? Does it make sense? So this is by just forcing the term on the viscous term to be 1. So that gives me a definition of what my delta is, that anchors the delta. So the flexibility I started in the beginning by assuming delta being an arbitrary function of x. All right. Okay, so now there is only one independent parameter in this equation. It is basically our original parameter a, right? We started with multiplied by c. We defined our original parameter a to be just the due over dx is proportional to a times ue, right? So this is basically related to that. All right, any questions so far? Yes?
Could you explain the memory aspect of the left-hand term?
The memory aspect of the left-hand side. So okay, So it basically comes from the momentum equation in the Navier-Stokes equation, right? And basically it's the momentum equation in a slightly tilted coordinate. And what this tells you is that if I have a change, so it takes a non-zero residual on the right hand side to change the boundary layer profile. And the more downstream you are, the harder it is to change that boundary layer profile. I mean, by 1 second is that we actually scaled, this C actually comes from scaling the viscous term to 1, right? So basically this says that as you go further downstream, it takes longer for the same viscous term to change the boundary layer profile. So if you have a bigger C, this term is more important, right? So you need the viscous force, which is here, is the same magnitude, to act longer, right? Act longer means you have to integrate the du dc for more C in order to achieve the same effect. One thing you can do is, one thing you can think of this equation is you can write the equation into du dc equal to some right hand side that doesn't depend on C. Also df dc at a right hand side, right? Then basically you are integrating in the C direction, starting from C equal to 0. Okay, so that's one way you can view this memory term or development term. Does that help? Okay, any other questions? Oh. Okay, it's good. So then basically we have an equation, right, that we can put into MATLAB to solve. And let's write down the equation just for clarity's purpose. So let's first start by this viscous term. We have d square u d eta square multiplied by 1. And let's then write out the pressure gradient plus, let me just call this parameter alpha prime. Okay, we have plus alpha prime times 1 minus u square. Okay, you can see everything becomes compact. And this is half of 1 plus alpha prime. Okay, plus half of 1 plus alpha prime times what? F times du d eta, right? F times partial u partial eta. Now it's partial derivatives because we also have C. That's the entire right hand side. And the left hand side is equal to C times the first term is df d eta, which is equal to what? Df d eta is equal to u, right? Is equal to u, is equal to u times du dc. The next term is df dc times du d eta. So let me write du d eta times df dc. So that's the equation we will be solving. All right.